Hello dear student, welcome to my class. So far we discuss geometrical optics, and in geometrical optics the ray travel in a straight line path and it is known as ray, and it is also known as ray optics. Clear? Now we will start another part of optics, that is known as wave optics, and in this case the wavelength of light is very similar as compared to the, if we compare the dimension of the object. Clear? So this is known as wave optics. So before we start wave optics, we have to know some basic idea regarding wave optics or history of light. There is vast history of light to know. The light is dual nature of light. It is known as dual nature of light. So what is dual nature of light? That means light sometimes behave as particle nature and sometimes behave as wave nature. Now we will start here wave nature of light. So what is wave nature of light? First we will discuss some basic characteristic, history of light. History of light. So first give some basic idea. Most important scientist, that is known as Newton, and according to his theory, this theory is known as corpuscular theory. And this corpuscular theory given by Newton in 1675. Clear? So according to the theory of Newton or corpuscular theory, light consists of a very small particle, and that small particle is known as corpuscle, and light consists very small or very tiny particle called corpuscles, and according to the theory, this theory is known as corpuscular theory. And here light consists of very thin particle and it is known as corpuscle, and its speed, which is equal to 3 into 10 to the power 8 meter per second. And again this corpuscle behave as a elastic property, and these corpuscles are rigid but weightless, negligible weight. Clear? And according to corpuscular theory, Newton proved that this corpuscular theory explains reflection, laws of reflection of light, rectilinear propagation of light, then refraction of light by using the concept of corpuscular theory. And he found that when a ray of light, when traveling from rarer to denser medium, according to this corpuscular theory, the velocity of light in denser medium is greater as compared to velocity of light in rarer medium. I am not telling that. This is the concept of Newton, and according to the Newton's corpuscular theory, velocity of light in denser medium is greater as compared to rarer medium. And he found that if there is a interface when a light incident at this point, and the light consists of corpuscle like this. Suppose this is one corpuscle like this direction, and it behave a that is elastic property, and due to this elastic property, after incident at this point, the corpuscles are reflected this direction, and he proved that angle of incident equal to angle of reflection. That means reflection law is proved. Next he proved rectilinear means rectilinear propagation. The corpuscle move in one medium which is straight line path. And refraction of light. What is refraction? Suppose there is a medium separated by two media. There is an interface, and this is rarer medium and denser medium. When light traveling from rarer to denser medium, because the particle inside denser medium are very strong and they form a large force with each other, and there is corpuscle like this. And when corpuscle present at the interface, due to this large force inside the denser medium, the force attract this corpuscle this direction in this way. Clear? Because it consists of number of particles, and due to this large force, this corpuscle, if you draw a normal here, change its direction like this. So when light incident on the interface separating by two medium, then the light bend towards normal, or the light bend from its original path due to this large force. Clear? And this large force due to the denser medium. Clear? But this theory is not convenience, or this theory is not properly describe the speed of light, because we know the particle in air medium they form a bound force, and that force is negligible as compared to denser medium. So this theory is not suitable for us, that is velocity of light in denser medium greater than velocity of light in rarer medium. After that, after 1 year, there is one important scientist known as Dutch scientist, and its name Christian Huygen, and he gave the theory regarding history of light in 1976, and he gave the light behave as a wave nature, and that wave is known as mechanical wave. But at that time Newton is a great scientist, so here the Huygen told that light behave as a wave, and that wave is known as mechanical wave, and that mechanical wave we already know. And this wave, mechanical wave, means just like sound wave, and when a sound wave travel in a medium, then it due to the propagation of, then due to the propagation means compression and rarefaction of the wave, and that wave is known as longitudinal wave. He found that this wave is longitudinal wave, and this wave is known as mechanical wave. And when mechanical wave travels, then there need a material medium, so there need a medium. But question may arise in mind, when light coming from sun to earth, then this is the direction of light in this direction. So while light coming from sun to earth, there is no medium, there is vacuum. So how light passes from sun to earth? Through this vacuum. And at that time Huygen told that if there is no any medium, there is one hypothetical medium, and that hypothetical medium is known as ether. Clear? And due to this ether medium, the light travel in the form of a wave, and it reaches from sun to earth. Clear? Okay. Then he also proved that when light traveling from rarer to denser medium, its speed decrease. While Newton said that when light traveling from denser to rarer to denser medium, the speed of light increase in denser medium. But according to Huygen, the velocity of light in rarer medium is greater as compared to velocity of light in denser medium, which is contrary to this method. Clear? But Newton is great scientist. He never told any type of, he don't take any type of mistake. But according to hygiene, here VR is greater than VD, and according to the wave theory of hygiene, he proved that is reflection of light, and we can say diffraction of light, and this law failed to explain polarization of light, and that is known as photoelectric effect. And at that time, another one scientist, that is Young's and Michelson-Morley experiment. This is the most important experiment. We will discuss here Young's double slit experiment, but Michelson-Morley experiment not in your syllabus. You will study in a higher study. So according to Young's double slit experiment and Michelson-Morley experiment, he proved that when light traveling from rarer to denser medium, the speed of light decrease. This is not increase. So that this theory is held to describe the nature of light. Clear? Because two scientists told that, here Young also told velocity of light in rarer medium is greater than velocity of light is denser medium. So corpuscular theory fail to explain the nature of light. Clear? And there is another one scientist also, after 150 years of this theory, there is another scientist known as Foucault, and he also told that velocity of light in rarer medium is greater than velocity of light in denser medium. Clear? And another one scientist at that time comes, that is Maxwell, and which is the most important scientist or famous scientist. According to this theory, light is nothing but the important characteristic that is known as electromagnetic wave. And this electromagnetic wave consists of both electric field plus magnetic field. When electromagnetic wave oscillate this direction, we already discussed, and suppose magnetic field inward direction, then this is the direction of speed of light. And when we already know, for electromagnetic wave there is not require any medium to travel the wave. So that type of electromagnetic wave is known as electromagnetic wave, require no medium. And the electromagnetic wave is known is so the characteristic of transverse in nature. But here Hygiene told that it is longitudinal nature. Actually it is not longitudinal nature, and it is the nature that is known as transverse nature. Clear? And he also derived that velocity of light in rarer medium is greater velocity of light in denser medium. Clear? So these are the characteristic, or these are the history of light. So we finally conclude that velocity of light increase. Here also velocity of light increase, and here also velocity of light increase. But Newton told that velocity of light while denser medium increase as compared to rarer medium, and this theory fails to describe the nature of wave, and corpuscular theory fail. After that, one scientist come whose name is Planck's quantum theory, and according to Planck's, when light traveling from a medium, it travels in the form of packet of energy known as packet. Planck's quantum theory you will study in your higher class. According to Planck's quantum theory, light consists of a packet, energy in packet, packet, and that energy in packet or packet energy is known as photon. Clear? And by using this concept, by using the concept of Planck's, another one important scientist, you already know his name, known as Einstein. In 1905, he proved that photoelectric effect, and here so that when a light fall on a metal surface, the electrons are ejected from the surface, and here the light behave as a particle nature. So here light behave as a wave nature, here also wave nature, and here also wave nature, electromagnetic wave. But Newton proved that the light is behave as a particle nature. So actually light behave which type of nature? It is finally concluded that light have both nature, that is known as wave nature, and that is another one nature, that is particle nature. So finally they conclude that the light behave as a dual nature, or dual nature of light we will study later class. So what is dual nature? Light behave particle nature, sometimes it behave particle nature, and sometimes it behave wave nature, and depends on the medium and surrounding condition. Clear? So these are the characteristic, or these are the history of light. Now we will study here the Huyen principle, and according to his principle we have to deal with light in the form of a wave, and here we will start wave optics. Clear? Now let's start wave optics. So we have to start from what is wave front. Suppose if we take a stone and this stone is thrown towards the pond, because there is still water, and if we observe from the top view, if we observe from the topmost point of the pond, and this still water, after throwing the stone inside the pond, there is still water, and if we observe from top view, then water, suppose this is water, this is pond, and this is top view. If we place a stone here, if we throw a stone here towards the still water, then here the wave travel in this direction, wave travel in this direction, the ripples of a wave travel in this direction like this, and here also this is the direction of wave in all the direction. Clear? These are the direction of wave in this way, and there is a stone. Now some of the water molecule which this is there was initially still water. After placing the stone inside it, then the water molecule, some of water molecule which vibrate with maximum amplitude and then minimum, maximum, minimum, maximum, minimum, and here also maximum, minimum, maximum, minimum, top, crest. In this way wave traveling or wave spread out all the direction in three-dimensional case. Clear? So if we join here the water molecule which vibrate with maximum amplitude, this point, and here also water molecule vibrate with maximum amplitude, this direction, and here also maximum amplitude, here also maximum amplitude. If you take another one wave is here like this, then here also the wave which vibrate with maximum amplitude like this point, this point. Clear? Now this is locus point, and here the locus point which vibrate with, we can write here like this. Clear? So this is locus point, another locus point, locus point. Now we have to join all the locus point. So this is wave. If we want to join all the locus point, then this is like a circle. So this circle is known as wave front. Wave front. So what is wave front? There is another point. If we drop the stone here, then the water molecule which vibrate with the maximum amplitude, then some of the minimum amplitude, maximum, minimum. This is the locus point of maximum amplitude, and there is another amplitude. This is minimum vibration, minimum trough. This is suppose crest. This is trough, 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 trough. If you want to join this all the trough, then it also form a wave front. Wave front. So what is wave front? The locus of all the point. Now joining the locus of all the point which are vibrating with same phase is called wave front. Locus of all the point which are vibrating with same phase. This is crest, this is crest, this is crest, crest. Then we have to take the locus point of particle which are vibrating with the same phase. That means we have to take the particle which are at crest. Then here also particle crest, here crest, and here also crest, here also crest. Then we have to join the topmost point of the particle. Then we get a circle, and the circle is known as wave front. And here all the particle vibrating with same phase, and that is known as wave front. Clear? So you can take another wave front here, another wave front here. These are the general, or these are the diagram of a wave front. Clear? And now if we disturb here, then the wave or ripples of wave, water wave, which travel in all the direction towards the direction. So this is the direction of propagation of wave. This is the direction of propagation of wave in this direction, all the direction. Clear? And these are the wave front. So this is the propagation of ray. It is propagation of wave. This is propagation of a wave, and this is wave front. And here the wave front is just like a circle. Clear? So depending on the nature of the medium, or depending on the nature of the source, the wave front is basically divided into three parts. There are three types of wave front. So first we will discuss, that is point source or spherical wave front. Spherical wave front. So what is spherical wave front? Suppose if we take a source here or light source here, then this light source give brightness in all the direction like this. And if you want to, and all the direction means the particle, suppose there is particle in this direction, also particle, here also particle, particle in all the direction, because wave travel in forward direction. While proceeding forward, the particles are moved spread in this direction. Now suppose this distance is r, this distance is r distance, and this is source point. Or you can say these particles are vibrating with same phase, and these are the locus of the similar phase. So now we have to draw a circle here, because it's three-dimensional figure. So this is just like a sphere. And you can take another particle here, this point, this point, this point, this point, this point, and this point. Then we get another sphere here. You can get another sphere here. So for point source, the nature of wave front, nature of wavefront is spherical. So what is the condition for which we get spherical wavefront? Spherical wavefront means if there is a point source and that point source gives us a spherical wavefront. And second type wavefront, it is cylindrical. Cylindrical wavefront. Suppose there is a linear source and this is one linear source, and if there is a point source, this point source give brightness all the direction. Suppose there is a linear source and it gives wave this direction, this direction, and this direction, this direction, in this direction. So we have to draw a circle here. Similarly, there is another circle, and finally we get another circle here. So this looks like a cylinder. Clear? So these are the direction of like this. These are the direction of propagation of wave. So propagation of wave, and this is just like a cylinder. So it is called cylindrical. Cylindrical wavefront. So how can we get cylindrical wavefront? If there is a for linear source, we get cylindrical wavefront. This is important. For point source we get spherical wavefront, and for linear source we get cylindrical wavefront. Clear? Another type of wavefront, that is known as plane wavefront. Planar or plane wavefront. So what is plane wavefront? Suppose this is point source. If you take this distance here, this is source like this, and here like this. Here radius increase. Now this is small radius, large, and again large, and here the radius of the wavefront increase gradually. If you take a large distance here, this is large distance, then here the curvature look like a straight line, like a straight line. Then at that time we get a plane wavefront, and this is known as a plane wavefront, like this here. This is plane wavefront. You can draw diagram like this. This is plane wavefront, and this is the direction of electromagnetic wave. So these are the direction of electromagnetic wave. Clear? And this is known as plane wavefront. And you have to keep in mind one thing, that the propagation of light wave always perpendicular to the direction of, or always perpendicular to the wavefront. This is suppose wavefront, and here the propagation of light this direction. Propagation of light and wavefront always make an angle 90 degree, and here also 90, 90, 90, and this is also spherical wavefront, and here the light propagate this direction, and angle between wavefront and propagation of light always 90 degree. So for plane wavefront, what is source here? Now source is here point source, but we have to measure, or we have to see for far distance or maximum distance from the point source, then we get a plane wavefront or planar wavefront. Or you can say this is cylindrical wavefront. There is another cylindrical wavefront here also. Particle vibrate in another locus point, and you can take another cylindrical wavefront here like this. So if you take large distance, then this wavefront look like a planar wavefront for large distance. Large distance, the wavefront like a planar wavefront. So what is the source of plane wavefront? Source of plane wavefront, that is known as point source, and here linear source. But we have to measure the distance, that is a large distance. For large distance, we get that is planar wavefront. Clear? So these are the characteristic of a wavefront. There is three type of wavefront: spherical wavefront, cylindrical wavefront, and planar wavefront. Clear? So what is wavefront? All the locus or all the particle which are vibrating in same phase called wavefront, or locus of the particle while we joining a line of locus of the particle which are vibrating with same phase, and that phase and that circle or sphere is known as a wavefront. Clear? So we conclude from the wavefront, the ray, the propagation of wave always perpendicular to wavefront. Clear? The propagation of wave always perpendicular to wavefront. And second thing, there is a source point, and this is wavefront, and this is also wavefront. First wavefront, second wavefront, but this is the direction of propagation of wave, because wave traveling forward direction, this direction, so this is the direction of wave. And here the angle between wavefront and propagation of wave always 90 degree. Clear? And the time taken, suppose there is another wavefront here, the time taken from the propagation from suppose this is S1, this is S2 and S3, first wavefront, second wavefront, and third wavefront. The time taken from S1 to S2, that is T, and then S2 to S2, that is also T. So the time taken by the propagation of a wave from one wavefront to another wavefront is same for same medium, but this distance and velocity may change. Distance and velocity may change if medium different. Clear? So this time here S1 to S2 time equal, and here S2 to S3 time also equal. Clear? And next thing, this is the locus of all the point. So we have to draw a spherical wavefront here like this. That means all the particle, all the phase of the particles in a wavefront. Suppose this wavefront, all the particle which are equidistant from the point source wavefront, all the phase of particle in a wavefront remain same, and so these are vibrating with constant phase difference. Clear? And here phase, and here phase, here phase, here phase is, if you want to find the phase here same, and phase difference between all these particles is 0. So these are vibrating with the same phase. Clear? So these are the important properties of the wavefront. Now we will start Huyen principle. Huyen principle. This principle is important. You have to remember this principle, and question may ask in your council examination, state the principle of, or state Huyen principle. So first principle, each source of light which behave as a disturbance or source of disturbance which starting in all the direction, and source of disturbance means a travel wave this direction, and travel wave this direction, and travel wave this direction, and this direction. And if we take the same distance, here same distance, here distance, and here distance, they form a wavefront like this. Clear? And here all the particle in the wavefront. This is one wavefront, and here particle, there is another point, here point, this point, and this point. This point particle which are vibrating with same phase, and their phase difference between the particle is always 0. Clear? This is first principle. Each source behave as a source of disturbance, and all the particle we have to take the equidistance which are vibrating with same phase. This is the principle of Huyen principle, and according to its principle, on the wavefront, and this is known as wavefront, and on the wavefront if we take a point here, then this point also make a wavefront like this. Clear? And this wavefront is known as wavelet. And this source is known as secondary source. Which produce wavelet. And the secondary source is also known as fresh source. Similarly, there is another point, it also make a wavelet, another point, it also make a wavelet like this. Clear? And this direction. And this is main source, this is primary source, and this is secondary source which form wavelet in this direction. So this is known as second rule. So second rule, what is second rule? On the point of a wavefront, each point behave as a secondary source or fresh source which produce wavelet. This is wavelet, and this is also one wavelet. This is wavelet, and this is also wavelet, and this is also wavelet. Next, third point. Now we have to draw a tangent on the wavelet like this, and if you draw a tangent here like this, here tangent, and this is also tangent, this is also tangent, and here also tangent. According to Huyen, now draw a geometrical envelope. Now we have to draw a envelope here like this. And this is known as geometrical envelope, or you can say if you join all the tangent of the wavelet like this, and if you join or if you draw a geometrical envelope, then this geometrical envelope is known as another one wavefront. This is known as again wavefront. Clear? And now draw geometrical wavefront or geometrical envelope, and this envelope is a wavefront. Clear? So there is another wavefront we get. Now this is also wavefront and there is another wavefront, and each point on the wavefront, then again you have to repeat this sentence. Then each point on the wavefront which behave as a secondary source, and due to this secondary source it produce wavelet, this direction. And now draw a geometrical wavelet or geometrical envelope in forward direction. Forward direction means this is wavelet, and here the wave traveling this direction, so this is forward direction. So we have to draw a envelope over the wavelet in forward direction, not inside direction or not inward. This is inward direction, but we have to draw a wavelet over the forward direction. Why? Because wave which traveling in forward direction, so we have to make a geometrical envelope over the wavelet. Now this geometrical envelope is known as the wavefront. And again we have to repeat this sentence. And on the wavefront, each point now behave as a secondary source, and due to this secondary source, wavelet again form this point in this direction, in forward direction. Now again we have to draw a geometrical wave envelope in forward direction. This is forward direction. Now this geometrical envelope is known as wavefront, and again on the wavefront we also know this point now behave as a secondary source and which form a wavelet, and in this way the wavelet travel in forward direction like this. Clear? And this is the propagation of wave this direction, and this is the envelope which give the concept of wavefront like this. Clear? So these are the most important concept of Huygen, and you have to remember this principle. First principle, I again my sentence. Each source behave as a source of disturbance, and if we take all the equal distance from the source point, then we have to draw a circle here, or we have to draw locus of all the points which are vibrating with same phase. Now this form a wavefront. And second thing, each wavefront or point on the wavefront, this point behave as a secondary source which form the wavelet. And if we draw the envelope, if we draw the geometrical envelope in forward direction, then we get a wavefront, and continue this process. These are the principle of Huygen. Now let's start superposition principle. Superposition principle. We already know superposition principle. Suppose there is a number of wave which traveling in a medium, and at a particular instant of time, suppose there is a wave y1 which is traveling in this medium, and another wave which is traveling in this medium y2, and second wave y3 traveling in this medium. In a medium there is a number of wave, and if you take a particular point, if all the wave are superimposed means one wave over the other. Now this direction, if you take this point, now there is another one wave which vibrate with this amplitude, and amplitude is here a. Now if we take another wave from this is y1, and second we have to take another wave, what is y2, now traveling this direction, and this displacement is again increased with, because here the first wave it's a1 and here a magnitude a2, and this maximum displace, this particle maximum displace at a particular point, that is we can write here amplitude a1 plus a2. Similarly, if there is a number of wave traveling in a medium, after superimpose each other, the final or the resultant displacement of the particle at a particular instant, at a particular point we can find by using the vector sum of all the individual displacement of the particle at that point. Clear? And suppose this wave, its amplitude suppose A1, and here amplitude A2, and here amplitude A3. Now we have to see this particular point here. When three rays are coming simultaneously and superimposed over each other, then here the particle which vibrate with maximum amplitude, which was this particle vibrate with this amplitude A1, and if this travel this A2, and when this ray travel here particle vibrate with A3. Now if three rays are simultaneously coming, then the total maximum, then the total amplitude which is A1 plus A2 plus A2, and this according to superposition principle, the net displacement of the particle at a particular instant of time, we can write the vector sum of all the waves, it is y2 plus y3 plus it is yn. This is known as superposition principle or principle of superposition. Clear? So by using this principle, we have to prove the interference phenomena. You already know what is interference. Interference means it is the distribution of light, and we have to find where the point give the maximum brightness, where the point give minimum brightness. So we have to find here two important property, that is maxima and minima property. And here for you already know that by using this principle of superposition, we get or we have to find the interference pattern. Or first we have to find here interference. So interference means the redistribution of light while a number of a wave or a two wave traveling in same medium with a single frequency, or you can say this wave or this two wave is known as coherent source. So what is the meaning of coherent source? Coherent source means the phase difference throughout the medium, the phase difference throughout the motion remain constant, and that wave is known as coherent source. So suppose there is a wave, what is y1 equal to a1 sin omega t, and another wave a2, that is sin or a you can write here amplitude a sin omega t plus phi. This is known as phase phi 1. You can write here this is phi 2. So phase difference phi 2 minus phi 1, which is equal to phi, or you can write here delta phi equal to phi. This is known as phase difference, and this phase difference always constant throughout the motion. Clear? So this is known as a coherent source. Coherent source. Coherent source means phase difference remain constant. So for interference we have to take a coherent source. So first suppose there is a source here, source S. Now you already know what is the meaning of constructive and destructive interference. We already discussed in your 11th syllabus or class 11. Suppose there is a wave like this in this direction, traveling this direction, and this is wave, that is y1, and second wave, there is another wave, this is y2. When they superimpose one another, when these two waves are superimposed, then here the amplitude A and here the amplitude also A. Now if we want to superimpose this wave, then final amplitude will be like this. Amplitude increase, and here amplitude increase, that is 2A. We already know intensity of light is directly proportional to square of the amplitude, and here intensity, that is I1, here intensity, that is I2, and here net intensity, here intensity suppose I1, here intensity I2. Intensity means brightness or glowness or maximum energy. So here intensity, that is you can write I net, which is directly proportional to 2A square, and which is I net equal to, we can write here 4A square, which was initially A square. Now intensity increased 4 times when two waves superimpose each other, and this condition is known as constructive interference. Similarly, if there is another wave like this, and this wave suppose y1, and here another wave, this wave is y2. After superimpose one another, then here this is maximum amplitude, that is A, and here maximum amplitude for downward direction, that is minus A. After superimpose each other, here also this is minus A and this is plus A. Superimpose each other, then you get a straight line. And because plus minus is 0, so I directly proportional to A square, this intensity is 0. When intensity of light, when intensity of source is 0, at that time we can say that this source is known as destructive interference. So we have to find constructive interference for maximum amplitude, destructive interference for minimum amplitude. And here crest and this point crest, trop, crest are match each other, trop also join each other. But here one crest and one trop get a destructive. One trop, one crest destructive. But here crest, trop which gets constructive interference, and crest, trop, crest which give destructive interference. So we have to find here interference. So for interference we have to use a single source. Suppose there is a source, or you can also write this is source S and wavefront traveling in all the direction like this. This is wavefront in this direction, and the wave travel perpendicular to the wavefront like this, and we have to use here a slit which have two fine holes. Clear? So here suppose this hole is S1 and here S2. This is known as slit. Now when this wavefront reach at the slit here, and we already know that on the point, each point on the wavefront which behave as a secondary source and it produce wavelet in all the direction. So here also now produce wavelet, this is wavelet, S1 source. Now here also produce wavelet, this S1, and this direction you can draw here like this. Clear? In this way. So you can draw, this is wavefront, there is also wavefront like this. Now again another wavefront, because some particle which vibrate with maximum phase difference, or some particle with crest and some particle with trough. So you can draw another diagram here. This is ray diagram. This is red symbol, and here also clear. Suppose there is a screen. This is screen. We have to observe here which point give the brightness, or which point is give the constructive interference, and which point give us the destructive interference. If we see clearly, then look at this point here. This point, and this point, another point, this point is here, and this point is also here, and this point here. This point. Clear? So we get a here this point. Clear? And again this point. Actually if you draw a clear diagram, then there is a straight line like this. That means here this is black line. The intersection of black line meet at a particular point. Black line and intersection of red line meet a particular point. Here this point is black line and red line. This line is red, this line, and here there is a point black line and this red line which lies in one point or one straight line, and this point is known as constructive interference. And here we get a brightness, and here we get a amplitude like this. This is constructive interference. Clear? And another one point we get the here the dark wave front and red wave front. Dark wave front, red wave front. Clear? And here dark wave front, red wave front. And this is the point of destructive. Means here destructive interference means there is no intensity, I equal to 0. This point, or you get like this wave here. So here the intensity is 0. And again, if you come the screen above the destructive point, then you get again the brightness, and again you draw a here, it is a darkness. And similarly below this point we get a, this is brightness, here darkness, and here brightness, and here darkness. This is T. So this point is known as central maxima. Clear? And this point is also known as, central maxima is also known as zero order maxima. This is also dark point, or this is known as fast brightness, or sorry, fast darkness, or fast order darkness, or fast order minima. Fast order minima after central maxima. Fast order minima, this is fast order maxima. Fast order, this point darkness, here intensity 0, and this point is known as destructive interference or minimum amplitude. So minima, this point is known as minima. Fast order minima after central maxima. And this point is also brightness, this is known as fast order, because this is 0 order. Central maxima 0 order, and this brightness is fast order maxima. This point is D, second order minima. Similarly this point D, dark, fast order minima after central maxima. This point is brightness, this point is known as fast order, this is also fast order minima. Fast order minima, this is fast order maxima, and this is second order minima. And again we get here the brightness, so this is known as second order maxima. So in this way we get the spectrum of light. So this is brightness, here darkness, brightness, darkness, here brightness, darkness, brightness, darkness, brightness, darkness. So these are the redistribution of energy, because here point source is energy. Now we get the redistribution of energy, and here we get maxima minima, darkness, sorry, brightness, darkness, brightness, darkness. These are the interference pattern. Clear? And here we have to use, this is one source and this is one source, and these two sources are coming from the central source, or this source is known as source of disturbance, and this is the primary source. Clear? So here we have to choose a frequency, angular frequency omega, and here angular frequency also omega. Why? Because frequency is the property of a source. If source change, then frequency also change, and there is a relation here omega, and this omega is constant. Clear? But phase difference between them is change. So now we have to find the constructive and destructive interference by using this concept.